Today on Macaulay Math, we're talking numerical integration using the trapezoidal rule. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 26 on numerical integration. Our goals for today. We're going to approximate a definite integral using the trapezoidal rule. We're going to approximate a definite integral using Simpsons rule. And we're going to analyze and approximate errors in the trapezoidal rule. The last few lessons have focused on the techniques used to integrate functions. To be clear, many functions cannot be integrated easily, and in some instances, not at all. Calculators that evaluate definite integrals don't even try. Calculators use a numerical method to approximate definite integrals because they are very good at making iterative, simple calculations and can do it much faster than a human. This lesson explores two techniques for approximating definite integrals using an iterative process: the trapezoidal rule and Simpsons rule. Let's get started. Definition: the trapezoidal rule. The trapezoidal rule approximates area under the curve over a given interval such that it is an approximation of the definite integral over the same interval. If f is a continuous function over the interval from a to b, then the definite integral can be approximated by, so here's my definite integral, and this expression is going to be my approximation. It's going to be b minus a, and b minus a is this upper and lower limit of integration divided by 2n, and that n is the number of subintervals over a to b. And so it's fairly simple. You're going to break it up into n equal pieces, and so you will have one more endpoint than n. So we're going to start with x sub 0, and basically what you do is you're going to plug in each of those endpoints into the function, and then you're going to go, the first and last one will just be the value of that function, and then every one in between will be times 2. I'm going to show you a quick demonstration on how we get this particular formula. Suppose there is a continuous function drawn here in yellow over a closed interval from a to b. Furthermore, suppose that we divide this interval along the x-axis into 4 equal subintervals. The length of these subintervals can be found by finding the difference of a and b, all divided by the number of intervals, in this case 4. From each of the subintervals, we draw 4 trapezoids shown here in green, with the height of the function being a base of the trapezoid and the width of the interval being the height. Clearly, this is a reasonable underestimate of the area under the curve. Now, we recall the area for a trapezoid is a equal to 1/2 times the height times the sum of base 1 plus base 2. For each of these trapezoids, we have an equal height. We'll call it h. Let the first base of the trapezoid be called b sub 0, the second base called b sub 1. Now, the first base of the second trapezoid shares a side with the first trapezoid, so its first base must also be b sub 1. Since this second trapezoid's second base is different, we're going to label it as base 2. Following the same pattern, we can label the remaining bases until we end at b sub 4. If we use all of this information and plug them into separate area of trapezoid formulas, then the sum of the formulas is an approximation for the area under the curve. Looking at the sum as a sequence, we can factor out a 1/2 h from each of those terms, and then we can combine like terms to get this expression. Now recall how h was calculated. It was the difference from a to b divided by 4. So let us use that to replace h. The bases can be calculated by plugging the x value at each of the subintervals into the function f. So let us replace those bases with function calculations. In our example, the number of subintervals was 4, but it can be any value. So let's replace the 4 with n and simplify. Now, look at the pattern for adding up all of the bases. The first and last value has a 1 for a scalar. All others are multiplied by 2. A generalization for n subintervals would look like this. Put it all together, and now we have the formula for the trapezoidal rule. Our first example, use the trapezoidal rule with n equal to 1 to approximate the value of the definite integral. All right, so the first thing that we want to do is we're going to find the heights of all of the trapezoids. So here's what we're going to do. We're going to take the difference of the upper and lower bound and divide that by 4. So I've got 1/4. That is my difference. So for me, it's just easier for me to draw a little number line here. And so my lower bound was 2, my upper bound was 3. I need to divide this into 4 equal parts, so I'm going to go equal parts there. And since they go up by 1/4, well, 2 is 8/4, so this would be 9/4. 10/4 would be 5/2. 11/4 would be there, and that won't reduce. And then 12/4 reduces down to 3. So here are our values. So this is going to be x sub 0, this will be x sub 1, this will be x sub 2, this will be x sub 3, and this will be x sub 4. So using the trapezoidal rule, we can say the definite integral from 2 to 3 of 2 over x squared dx is going to be approximately equal to 3 minus 2 over 2 times n. In this case, n is 4. And then what we're going to calculate is we're going to say that it is f of 2 plus 2 times f of 9/4 plus 2 times f of 5/2 plus 2 times f of 11/4. And now, since 3 is the last one, it's just going to be plus f of 3. Now, plugging into the original equation, I get 1 over 8. 3 minus 2 is 1. 2 times 4 is 8. And then when I plug in, I'll have 2 over 2 squared plus 2 times 2 over 9/4 squared plus 2 times 2 over 5/2 squared plus 2 times 2 over 11/4 squared plus 2 over 3 squared. Now, I put all these into a calculator and it spits out for me 0.335. And that's pretty darn close, because if we go to Desmos and we bring up our keyboard, go to functions, go over to MISC, down here is a definite integral, and we want to go from 2 to 3 of our function, which was, well, we'll need parentheses around it, 2 divided by x squared. And then we want to close those parentheses and go dx, and it will calculate it. So the exact value is 1/3, and we came up with 0.335. So it looks like we were a little bit over. Simpsons rule. Now, Simpsons rule is another method for numerical integration. I'm not going to do a demonstration because while it is different, the example that I gave for the trapezoidal rule is close enough for us to see a pattern. For the trapezoidal rule, n could be any positive integer, but for Simpsons rule, n must be an even number. The reason that that is true is because for this to work, we have to start with f. The first one will be 1, and then it's going to alternate 4 and 2, 4 and then 2 until you get to the last one. And the one before it will be a 4, and the last one will be a 1 again. And I'll show you what that means here shortly. But it becomes fairly obvious. And then the value out front is going to be b minus a all over 3n. So let's do an example of Simpsons rule. So here I say use the Simpsons rule with n equal to 8 to approximate the value of the definite integral. So here again we're going to try and find delta x first. the upper limit, which is 8, the lower limit, which is 0, divided by n, which is also 8. So we're going to get 1. I draw myself a little interval here. I have 0 to 8, and I need 8 intervals. That's an even number, so I'm going to divide it in half. Divide those both in half. Now I got 4. We'll divide all of those in half. Now I'm going to have 8. So if it's 1 over, I start with 0. It'll be 1, 2, 3, 4, 5, 6, 7, 8. And this 0 will be x sub 0, x sub 1, x sub 2, x sub 3, and so forth until I get to x sub 8. All right, so my integral from 0 to 8 of x squared plus 1 dx is going to be approximately equal to 8 minus 0 over 3 times 8 times, it will be f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3 plus 2 times f of x sub 4 plus 4 times f of x sub 5 plus 2 times f of x sub 6 plus 4 times f of x sub 7 plus, now since it's the last one, it'll just be f of x sub 8. Now, me plugging all of those in, this expression here, I'll get, my 8s are going to cancel because 8 minus 0 is going to be 8, and then 8 over 8 is 1. So I'm going to have 1/3 out front, and then I have to plug in these values into this expression. So my first term will be 0 squared plus 1 plus 4 times 1 squared plus 1 plus 2 times 2 squared plus 1 plus 4 times 3 squared plus 1 plus 2 times 4 squared plus 1 plus 4 times 5 squared plus 1 plus 2 times 6 squared plus 1 plus 4 times 7 squared plus 1 plus 8 squared plus 1. Now, I went through and did all these calculations by hand on a separate sheet of paper, multiplied by 1/3, and I got 536 all over 3. And that is my value there for my approximation. And you can plug that into Desmos, and it'll show you that you get a pretty good approximation. The last definition here, we have the error approximation for the trapezoidal rule, provided that f has a continuous second derivative on the interval a to b, then the error e in approximating the definite integral by the trapezoidal rule is going to be the error has to be less than or equal to the difference of the lower and upper bound of integration cubed over 12n squared times the maximum value over the second derivative of that same interval. So you're going to have to find the second derivative, and then you're going to have to find the maximum value on that. And we're just going to use a graphing calculator to do that. In general, the way that this is used in the quote-unquote real world is if you know what you want your error to be less than or equal to, you can use this calculation to figure out how big your n has to be. So if you want your error to be less than 10%, if you plug in all of these values, you can figure out what n will have to be that. And so the smaller you want the error, the bigger your number of values have to be. So let's do a quick example. It says, estimate the error in using the trapezoidal rule in the definite integral from the first example knowing that n equal to 4. All right. And so the first thing I have to remember is we'll bring that equation up and we'll say that the absolute value of the error has to be less than or equal to b minus a all to the third power over 12n squared. And then that is going to be multiplied by the maximum absolute value of the second derivative. All right, so I have to find the second derivative of this. So if I have f of x is equal to 2x to the negative 2, then I reduce this exponent by 1, I'll get x to the negative 4, and that's equal to 12 over x to the negative 4. So I'll go back to my Desmos, and so here we see f of x equal to 12 over x to the 4th. Now, if I look at that graph, it is decreasing all the way from 2 to 3. So my maximum value is going to be here at that endpoint in this particular case. And so if I go 2 comma f of 2, and we tell it to label that, at 2 I get 0.75. All the rest of the values till I get to 3. So over the interval that we're talking about will be less than that. So 0.75 is going to be the maximum value of that second derivative. So I go back to here and I plug in everything I know. So this thing will be less than or equal to 3 minus 2 to the third over 12 times 4 squared times 0.75. And again, that 0.75 is the biggest value over the given interval of this second derivative. And when I plug all of this into a calculator, it ends up being less than or equal to 1 over 256, which is a very small error. It's pretty close. Well, that's all I got for today, folks. So, the Star Wars fun fact of the day. In Star Wars Rebels, the animated series, Kanan Jarrus is one of the lead protagonists who has a lightsaber, but he is not a Jedi Knight. During Order 66, the Purge of the Jedi Order, he was merely a Padawan learner, and he has hidden his abilities right up until the first episode of the show. And this picture is at the end of the show after he's lost his sight, but up until that point, he was just a Padawan. So that's all I got for today, folks. Have a good day. Bye.